Welcome to part 3 of our camera training series, Image Formation. Every image captured by a camera is shaped by how light enters the lens, reaches the sensor, and is converted into a visible frame. In this video, we will explore the key principles that influence image brightness, sharpness, motion clarity, and overall visual quality. Understanding image formation is essential for selecting and configuring reliable cameras for unmanned ground vehicle applications. Let us begin. We begin with frame rate, or FPS, which determines how many images the camera captures every second and how smoothly motion is displayed. Next is exposure time, which controls how long the sensor collects light for each frame, affecting brightness and motion blur. We will then compare global and rolling shutters and understand how they capture moving scenes differently. The lens aperture controls the amount of light entering the camera and influences image brightness. We will also explore fixed, automatic, and manual focus types and where each is best suited. Next, we will understand depth of field, which determines how much of the scene remains sharp. Lastly, we will explore the image signal processor, or ISP, the critical processing stage that converts raw sensor data into clear, usable video. Let's get started. Let us begin by understanding frame rate, commonly measured in frames per second, or FPS. A video is not one continuous image, it is a rapid sequence of individual pictures called frames. For example, a camera operating at 30 FPS captures 30 separate images every second. When these frames are displayed quickly, they create the appearance of smooth motion. A lower frame rate makes movement look jerky, while a higher frame rate produces smoother video and captures moving objects more frequently. For unmanned ground vehicle cameras, FPS directly affects navigation visibility, obstacle tracking, bandwidth, processing load, and storage requirements. This image compares how the same landscape is captured at 5, 10, and 15 frames per second over a 1-second interval. At 5 FPS, only 5 images are captured, so the movement between frames is larger, and the video can appear jerky. At 10 FPS, the camera captures twice as many frames, making the motion more continuous and easier to follow. At 15 FPS, the frames are much closer together, producing smoother motion and better visual tracking. The key point is simple. A higher FPS captures movement more frequently, improving smoothness, situational awareness, and navigation quality for a moving vehicle. Let us now see how frame rate affects the way motion appears in a video. In this demonstration, the same car travels through the same landscape at 4 different frame rates: 5, 10, 15, and 20 frames per second. At 5 FPS, the movement appears noticeably jerky with larger jumps between frames. As the frame rate increases to 10 and 15 FPS, the motion becomes progressively smoother and easier to follow. At 20 FPS, the car's movement appears more continuous and natural. This comparison clearly shows how increasing FPS improves motion smoothness and visual clarity.
Modern movies and premium television shows are commonly produced at 24 frames per second or 24 FPS. This means the camera captures 24 individual images every second. 24 FPS is widely used because it provides smooth enough motion while preserving the familiar cinematic look, including natural motion blur. The frame rate is first selected during filming, then maintained by the editing team, broadcaster, or streaming platform. When played on a modern TV, the television displays the program using the original 24 FPS timing, unless motion processing settings create additional frames.
This table shows the estimated storage required for a full HD video. The rows represent different frame rates from 10 to 30 FPS, while the columns show recording durations from 10 to 90 minutes. As the frame rate increases, the assumed bitrate also increases, which means the video requires more storage. For example, at 10 FPS, a 60-minute recording needs about 1.5 gigabytes. At 30 FPS, the same duration requires around 4.5 gigabytes. The key takeaway is that higher FPS gives smoother motion, but it also increases bandwidth, processing load, and storage requirements.
This table estimates the storage needed for continuous full HD video recording using H.264 compression. The rows show frame rates from 10 to 30 FPS, while the columns show recording durations from 10 to 90 days. As frame rate increases, the assumed bitrate also rises, so storage requirements increase significantly. For example, one camera recording at 10 FPS needs about 1.08 terabytes for 30 days. At 30 FPS, the same period requires approximately 3.24 terabytes. The key takeaway is that smoother video demands more storage, and for multi-camera vehicles, the total requirement increases with every additional camera. Let's take a quick look at our agenda. We have now completed our discussion on frame rate, or FPS, and understood how it affects motion smoothness and video performance. Let us now move to the next topic, exposure time. We will understand how long the camera sensor collects light for each frame, and how this influences image brightness, motion blur, and overall clarity.
Let us now understand exposure time, also known as shutter speed. Exposure time is the duration for which the camera sensor collects light to create a single frame. It is expressed in fractions of a second, such as 1/30th, 100th, or 1/500th of a second. In the comparison shown here, the longer exposure of 1/30th second produces a brighter image, but movement and vibration create visible blur. The shorter exposure of 1/500th second captures the rocky terrain much more sharply, but the image becomes darker. So exposure time is always a balance between image brightness and motion clarity. This image shows how shutter speed changes a UGV camera view while moving across rough terrain. At slower settings, such as 1/30 or 1/60 second, the image is brighter, but motion and vibration create noticeable blur. As the shutter speed increases to 1/250, 1/504/1000 second, the terrain becomes progressively sharper and movement is frozen more effectively. However, the image also becomes darker because the sensor collects light for less time. The key is to balance brightness with motion clarity for reliable vehicle navigation.
A histogram is a graph that shows how an image's brightness is distributed from dark shadows to bright highlights. This image shows how a histogram helps us judge exposure in a camera view. On the left, the underexposed image is too dark. Most histogram data is pushed toward the shadows, causing important terrain details to disappear. In the center, the correctly exposed image shows a balanced histogram spread across shadows, midtones, and highlights. This preserves useful detail throughout the scene. On the right, the overexposed image is too bright. The histogram is pushed toward the highlights, and bright areas lose detail. For vehicle cameras, the aim is not a perfect histogram, but to preserve critical information in the terrain, obstacles, and targets. This section provides a general photography reference for selecting shutter speed based on the type of motion being captured. Very long exposures, such as several seconds or minutes, are used for star trails or blurred water. For slower human movement, around 1/1 cn25 second is suitable, while waves may require about 1/250 second. Faster subjects, such as sports, vehicles, and flying birds, need much shorter exposures, from 1/500 second up to 1/2000 second, to freeze motion clearly. For vehicle navigation cameras, shutter speed should match the vehicle's speed, terrain, and available light. For a stationary or slow-moving UGV, 1 by 60 to 1 by 125 second can provide a brighter image. For normal navigation, 1 by 125 to 1 by 250 second offers a good balance between brightness and motion clarity. On rough terrain or at higher speeds, 1 by 250 to 1 by 1000 second helps capture sharper obstacles and ground details, though it requires more light. For most vehicle operations, 1 by 125 to 1 by 500 second is a practical working range.
A camera shutter controls when and how the image sensor is exposed to light. In traditional cameras, it works like a physical curtain that opens briefly and then closes. In digital cameras, this function is often performed electronically by the sensor. As we have seen before this, the shutter determines the exposure time for each frame. A longer exposure collects more light but can create motion blur, while a shorter exposure freezes movement more clearly but may produce a darker image. In modern cameras, shutter design also determines whether the full frame is captured at once or scanned line by line. We will see this in more detail in the coming slides. Shutter type describes how a camera sensor captures each frame. For the global shutter, all pixels are exposed at nearly the same time, so the entire image represents one instant. This keeps poles, vehicles, and terrain features straight, even when the vehicle is moving or vibrating. With a rolling shutter, the image is captured row by row. Because each row is recorded at a slightly different time, fast movement can create bending, skew, or wobble. For vehicle navigation and perception, especially on rough terrain or at higher speeds, a global shutter is generally the better choice. A global shutter captures all pixels at nearly the same moment. Its main advantage is accurate motion capture, with minimal bending, skew, or wobble. This makes it ideal for moving vehicles, rough terrain, obstacle detection, and machine vision. However, global shutter cameras are usually more expensive and may offer lower low-light performance than comparable rolling shutter sensors. A rolling shutter captures the image row by row. Its advantages are lower cost, wide availability, and often better resolution or sensitivity. However, fast movement and vibration can distort poles, vehicles, and terrain features. For vehicle navigation, global shutter is generally preferred, while rolling shutter is better suited to slower or more static applications.
We have now completed exposure time and shutter types. Let us move to the next topic, lens aperture. We will explore how the aperture controls the amount of light entering the camera and how it influences image brightness, sharpness, and depth of field.
Aperture is the adjustable opening inside a camera lens that controls how much light reaches the image sensor. It is measured using f numbers, such as f by 1.4, f by 2.8, or f by 8. A smaller f number means a larger opening, allowing more light into the camera. A wider aperture produces a brighter image and helps in low light conditions, but reduces the depth of field. A smaller aperture allows less light, but keeps more of the scene in focus. For vehicle navigation cameras, aperture must balance brightness, low light performance, and terrain sharpness. Let us understand how modern navigation cameras use a fixed aperture lens. The aperture is built into the lens and selected during camera design, typically with values such as f by 1.8, f by 2.0, or f by 2.8. Unlike a DSLR lens, it usually does not open or close while the vehicle is operating. This fixed design improves ruggedness, reliability, and calibration stability, which are especially important for automotive and vehicle camera systems. Here we explain how a navigation camera manages changing light while keeping the aperture fixed. As the vehicle moves from bright sunlight into shade, the camera adjusts shutter speed, sensor gain, and HDR or ISP processing to maintain a usable image. A fixed aperture is common because it has no moving iris mechanism, making the camera more rugged, reliable, and easier to calibrate. This gives predictable performance in sealed automotive and vehicle camera systems.
Let's take a quick look at our agenda. We have now completed lens aperture and understood how it controls the amount of light entering the camera. Let us move to the next topic, focus types. We will look at fixed focus, autofocus, and manual focus and understand where each approach is best suited in a camera system.
Focus determines whether objects in an image appear sharp or blurred. A camera achieves focus by directing light from the subject so that it converges correctly on the image sensor. There are three main focus types. Fixed focus is preset and has no moving mechanism, making it rugged and reliable for vehicle navigation. Autofocus adjusts automatically when subject distance changes, but it may hunt or select the wrong object. Manual focus is adjusted by an operator and is useful during setup or long-range observation. For most navigation cameras, fixed focus is preferred because it's simple, stable, and dependable. Fixed focus means the lens is preset to a specific focus position during design or installation and does not continuously adjust while the vehicle is operating. Using a wide-angle lens and suitable aperture, the camera can keep near-ground detail, mid-range obstacles, and distant terrain acceptably sharp at the same time. This makes fixed focus ideal for navigation cameras because there are no moving focus parts. The result is a simple, rugged, and low-maintenance design with stable calibration and predictable performance under shock and vibration. Its limitation is reduced flexibility for extreme close-ups or major zoom changes.
Let's take another look at our agenda. We have now completed focus types and understood the differences between fixed focus, autofocus, and manual focus. Let us move to the final topic in this section, depth of field. We will understand how much of a scene remains acceptably sharp and how lens settings and object distance influence the visible focus range.
Depth of field, or DOF, describes how much of a scene appears acceptably sharp at the same time. A camera focuses most precisely at one particular distance, called the focus point. However, objects slightly nearer and farther away may also appear clear. In the comparison shown here, a shallow depth of field keeps only a limited region sharp, while the foreground and background become blurred. A deep depth of field keeps a much larger range, from nearby ground details to distant terrain, clear and usable. Here we explain the main factors that affect depth of field. A wider aperture creates a shallower focus range, while a smaller aperture keeps more of the scene sharp. Longer focal lengths usually reduce depth of field, whereas wide-angle lenses and greater focus distances increase it. For vehicle navigation, this is important because the camera must clearly show nearby ground, mid-range obstacles, and distant terrain. That is why a deep depth of field is generally preferred for fixed-focus navigation cameras. Let's understand what affects DOF. A wider aperture creates a shallower depth of field, so less of the scene appears sharp. A smaller aperture gives a deeper depth of field, keeping more of the scene in focus. Similarly, longer focal lengths reduce depth of field, while wide-angle lenses and greater focus distance increase it. Today, most navigation cameras use fixed focus, and often a fixed aperture, to achieve a deep, usable depth of field. This makes the camera rugged, reliable, stable over time, and well-suited for consistent vehicle navigation.
Let's take one last look at our agenda. We have now completed depth of field and understood how much of a scene can remain acceptably sharp at the same time. Let us now move to the next topic, the Image Signal Processor, or ISP. We will see how the ISP converts raw sensor data into a clear, balanced, and usable image. Before we begin to understand what a ISP does, let us understand where an ISP sits in the flow of image capture. Let us understand where the ISP fits within the complete camera video pipeline. The process begins with the real-world scene. The lens focuses incoming light onto the image sensor, which converts that light into electrical signals. At this stage, the output is still raw sensor data and is not ready for viewing. This is where the image signal processor, or ISP, becomes critical. The ISP converts the raw Bayer pattern data into a clear and usable image. It performs demosaicing, controls exposure and gain, corrects white balance, reduces noise, improves HDR performance, corrects lens distortion, and adjusts color, contrast, and sharpness. Once the image has been processed, it is sent to the H.264 or H.265 encoder. The encoder compresses the video so that it can be transmitted efficiently over the network. Finally, the video reaches the ground control station display. Let us now understand the ISP, or Image Signal Processor. The ISP is one of the most important processing elements inside a digital camera. Its job is to convert the raw data captured by the image sensor into a clear and usable image. As shown in the image, the process starts with the raw sensor input. At this stage, the sensor sends basic pixel information, which is not yet ready for display. The first major step is demosaicing. Most color sensors capture red, green, and blue information through a Bayer pattern. Demosaicing combines this data to create a complete color image. Next, exposure and gain control adjust the brightness. This is especially important when a vehicle moves between bright sunlight, shadows, tunnels, or low-light areas. White balance then corrects the color tone so that objects appear natural under different lighting conditions. The ISP also performs noise reduction. This helps reduce grain and unwanted visual noise, particularly in low-light images. After this, HDR or WDR processing improves visibility in scenes that contain both bright and dark areas. For example, it helps the camera see a shaded road without losing detail in the bright sky. The ISP can also correct lens distortion. Wide-angle cameras may bend straight lines near the edges, and the ISP compensates for this effect. Color, contrast, and sharpness are then tuned to improve image clarity and make important features easier to identify. Finally, the processed video is sent to the encoder. So, the complete flow is simple. The lens and sensor capture the scene, the ISP cleans and optimizes the image, and the encoder prepares it for transmission or recording. In a vehicle camera, a well-tuned ISP can significantly improve navigation visibility, operator awareness, and computer vision performance. Let us now understand a couple of ISP topics which we have not covered before. Starting with demosaicing, a camera sensor does not capture full color at every pixel. Instead, each pixel records only one color, red, green, or blue, using a Bayer pattern. In this example, the camera is viewing a vehicle moving through an outdoor landscape. The sensor first captures the scene as a grid of red, green, and blue samples. The demosaicing process then examines the neighboring pixels and estimates the missing color information at each location. By combining these nearby red, green, and blue values, the ISP reconstructs a complete RGB value for every pixel. The result is the final full-color image, where the sky, terrain, vegetation, rocks, and vehicle appear naturally colored. In simple terms, demosaicing converts the sensor's color mosaic into a complete usable image.
Let us now understand the last topic in ISP: lens distortion correction. Wide-angle cameras are useful on vehicle because they provide a larger field of view. However, they can also introduce barrel distortion, where straight lines near the edges appear curved and objects may look stretched. The ISP corrects this using lens calibration data. It first identifies the lens model and the amount of distortion present. It then remaps the affected pixels and straightens the image geometry. As a result, the trail edges, horizon, rocks, and surrounding terrain appear more natural and accurate. This corrected image gives the operator and navigation system a better representation of the real scene, improving obstacle detection, distance judgment, and overall driving confidence.
This brings us to the end of Part 3, Image Formation. In this video, we explored frame rate, or FPS, exposure time, global and rolling shutters, lens aperture, fixed, automatic, and manual focus types, and depth of field. Together, these parameters determine how a camera captures motion, controls light, maintains focus, and produces a clear and usable image. In Part 4, we will move on to image quality and examine the factors that influence camera performance under real-world operating conditions. Thank you for watching. I hope you found this video useful and enjoyed the session. See you in Part 4.